So, hello, welcome to the continuation of Chapter 6. Um, Honestly, I kind of already covered all the equations for Chapter 6. Conservation momentum is P equals mv, or P initial equals P final. You just got to keep track that V, and therefore P, is a vector. That doesn't mean I don't have a full day of class planned. I still do. It's just going to be a few example problems and me showing how this can become complicated. So, any questions before I start up? Okay. So I said I started last time with a problem that's a little complicated. I said I would do a more traditional problem. Before I add more to the conversation, I'm going to do two problems that are old exam problems. These, as I said, will be most similar to what's like on an exam. And this traditionally is some of the easier problems I put on exams because they're pretty straightforward. And my problem is Mario, when riding his faithful steed Yoshi, tries to jump over a bottomless pit. However, Mario realizes that he isn't going to make it, and so he jumps off. This is a thing you could do in the Super Nintendo, Super Mario Brothers, and a few others since then, but basically, you're riding Yoshi, you're not going to do a jump, you can jump off. Yoshi goes downwards, and you can go up and get extra height. Let's say initially Mario and Yoshi are initially falling straight downwards at 5 meters per second. And when Mario jumps off Yoshi to get some extra height and distance, Mario leaves Yoshi with a speed of 8 meters per second. How fast is Yoshi plummeting to his doom? There's the question. What you should do with these problems is, like always, kind of collect your notes. And what I can say is I know the mass of Mario, I know the mass of Yoshi, and I know the initial velocity of both of them. I'm not going to say VYI and VMI. I'm just going to say VI because initially they're both traveling downwards at a rate of 5 meters per second. That means my initial velocity is the same for both of them. But I got to keep track of vectors. They're initially going downwards. And because they're going down, I'm going to say their initial velocity is negative. Afterwards, Mario jumps off and Mario goes at 8 meters per second. Therefore, the velocity of Mario final is 8. And I want to know the velocity of Yoshi final. So there's my figure. Initially, they're both falling. Afterwards, Mario's going up, and we're going to kind of assume Yoshi's going to go down, but we're going to solve for that. And the general idea in these problems is just that initial momentum equals final momentum. And well, momentum is mv. Now, in this case, they were both moving together. This is kind of like a completely inelastic problem, but backwards. It's just instead of them starting apart and going together, it's them starting together and coming apart. Though you can do problems the other way also. And I sometimes give problems like that. But what I can say is they both have the same initial velocity. And what I'll do is I'll just treat the initial as one object. I'll say initially, I have one thing that has a total mass of Mario plus Yoshi, and it's going downwards with some initial velocity. I would say this is one set unit that is at this velocity. And so since momentum equals mv, which I realize I never actually made show up on this slide, that was silly of me, I'll say that my initial momentum equals my final momentum. Then I'll just look at my picture and say initially I have these two together. Final, I have Mario, and final, I have Yoshi, and I'll just add them all up. That is how I solve these problems. You just write an equation for initial momentum and final momentum. Well, really, it's just mv of each thing added up. Now, I could have done it separately. I could have put it as, what is it? Mass Mario velocity initial plus mass Yoshi velocity initial and kept them separate and just said they had the exact same magnitude. That would have worked. You can really go either way. Now, my goal here is to find Yoshi's velocity. At this point, it's just algebra. If I want to get this term, what I'll do is I'll start by subtracting Mario's final momentum from both sides. And once I subtract Mario's final momentum from both sides, I can divide both sides by the mass of Yoshi. Which leaves me with just plugging in and solving. Now it's of note I got a negative answer, but that makes sense. Negative just means down. It means Yoshi's going downwards, which was kind of said in the problem. Need to add a GIF to this slide of actual in the game, not just the video mocking it. Any questions though? Let's do one with a bounce instead. This problem says, Magneto floats towards the X-Men at 2 meters per second. Someone throws Wolverine at Magneto, which is a thing that happens in the comics all the times. And Wolverine gets thrown at 15 meters per second. Magneto, seeing Wolverine flying at him, uses his power to just shoot Wolverine away. There's a lot of metal in there. He just repels it. And afterwards, Wolverine moves backwards at 8 meters per second. Given both of their masses, and Wolverine weighs quite a bit because of a metal skeleton, how fast does Magneto move afterwards? Basically, this is my problem. I kind of swapped the colors here, but this red one will be Wolverine, who weighs more. He's coming in. That did that. Okay, let's try it again. And they'll bounce off each other. Magneto might be pushing Wolverine. Magneto here being the blue. But the question is, how fast does Magneto go afterwards? Just looking at it like that. See, what I can say is this is a collision. This is conservation of momentum. And I'm going to shrink the text a little bit for space reasons. And I'll collect my notes. I'll say initially, Magneto is moving at 2 meters per second. And once again, you got to be really careful with subscripts for momentum because there's going to be a shit ton of them. There's only going to be more as I get further. And I'll say initially, the velocity of Magneto initial was 2 meters per second. I can then say Wolverine was moving at 15 meters per second. But let's look at my picture. He's moving to the left. Since in my picture he's to the left, I have to say it's negative. That's where the people go wrong most often on these problems, is they forget to make velocities negative. Make sure you do. I then say after the collision, Wolverine goes backwards at 8 meters per second. But look at my picture. Backwards for him is to the right. So that's a positive value again. And so my velocity of Wolverine final is a positive value. And I gave the mass of Wolverine and the mass of Magneto. And I asked for the velocity of Magneto final. Everyone following? So at this point, yes. I'm going to hit what... Oh, sorry. That is a yes? Okay.
Yeah, that was a yes.
Okay. So at this point, I'm going to just get rid of all the text. I don't really need it. And say what I know is conservation momentum. Initial momentum equals final momentum, where momentum is mv. And looking at this picture, I can't group people together like the last one. I can say initially there's a Magneto moving, initially there's a Wolverine moving. Final, there's a Magneto moving. Final, there's a Wolverine moving. So I'll just say mv for Magneto initial plus mv for Wolverine initial equals mv for mv for Magneto final plus mv for Wolverine final. Now my goal for this one is to find this tool is to find the velocity of Magneto final. And so I just need to rearrange and solve for that. I'll subtract Wolverine's final momentum from both sides. And then I'll divide both sides by the mass of Magneto. Once I have that, it's simply plug in my numbers. And once I plug in my numbers, I'll get a value. Now note it's a negative value, and it's really goddamn fast negative value. The negative makes sense. He's to the left. That matches with what I showed here. And I mean, just look at this video when I play it. The blue car goes a lot faster off than the red one. It's because he weighs a hell of a lot less. That flinging someone like this would only send him shooting through the air quickly. mostly because of Newton's third law. That is how you do these problems in those simplest form. Really, it's how you do them in the most complicated form too. The most complicated form just adds a layer of annoyance, which is what we'll do starting on the next slide. But if anyone is lost here, let me know before I make it complicated. Okay. So these were pretty straightforward. Everything was a vector because we're just like, hey, look, things go, they bounce off each other. But let's say instead, I hate when my mouse disappears. I look at this situation. Here, when I have it hit not straight on, but off to the side, what I'm getting is that the two things are separating. That instead of just boom, I have deflections. And if momentum is a vector, when this bounces and starts going this way, if I was looking at this from above, it would make more sense. My final has a vector this way, a vector that way, while my initial had just the one thing moving here. What happens when I do this is if I want to do the vector, I'm going to be like, oh, we got to look at directions. See, in all the problems we did so far in 1D, I didn't have to worry about that because I was just said to the right is positive, to the left is negative. Up is positive, down is negative. But if the collision starts moving in 2 dimensions, we have to keep track of the fact it's 2 dimensions. And basically, we're going to do the same shit we did in the past with this. I'm going to say if I have this collision, and this picture to the right is basically the same thing, I'm going to say if we have 2 dimensions, if instead of boom, we have boom, what I need to do is break it to 2 problems. Instead of just initial momentum equals final momentum, I'll say the initial momentum in x equals the final momentum in x. The initial momentum in y equals the final momentum in y. And any velocities I'm given, I'll split them to the x and y components. That instead of saying I have a velocity up in this way, I would say screw that noise. I have 2 velocities, the x component and the y component respectively, and just treat it as 2 separate problems. If we're in 2 dimensions, instead of just m1v1 initial plus m2v2 initial equals m1v1 final plus m2v2 final, I'm going to have one of those for x and one of those for y, which makes I have even more subscripts to deal with, which is annoying, but kind of a fact of these problems. And so what you're going to need to do is just go and separately solve the x's and y's. What you do is just take your initial problem, the pictures that you draw or I give you, depending on what it is, and you start by just taking every velocity and breaking it into components. And once you have all your velocities and components, say, you know what, this is 2 separate problems, 2 unrelated, uncoupled problems that I'll solve both of. Once you get that, if I ask for magnitude and direction, you can put them back together with a little bit of trig. Okay. So I'm going to do 2 of these. And just like before with the 2D, I did a completely inelastic, though I did an opposite where they started together and broke apart. I'm going to do a completely inelastic where they start apart and come together. And I'll also do one that isn't, where things are bouncing off each other. Well, basically my one where they're bouncing off each other is this. Come on, go again. Is this exact situation. So let's do these problems. This is not one I wrote. This is a textbook problem, but you know what? Sometimes I'm lazy. And it says, peregrine falcons hunt by grabbing the prey from above. What happens is the falcon will see something it wants to eat and will fly down and just grab onto it. Let's say a falcon is flying at 18 meters per second and goes downwards at a 45-degree angle from behind on a pigeon. This pigeon is traveling perfectly horizontal at 9 meters per second. Given the mass of both of them, what is the speed and direction of the falcon immediately after grabbing the pigeon? So here is my oh so fancy pictures. I initially have a falcon moving at 18 meters per second. And this 18 meters per second is the velocity of falcon initial. It's at 45 degrees. I actually labeled it as negative 45 just so I can remember it's below the horizontal. I could have just done 45 also and remembered to make my y component negative because it's down. It works either way. The pigeon is initially moving horizontally at 9 meters per second. This doesn't need to be broken into components because he's moving to the right. So that's at the x-axis. So I won't have to worry there. Now, as long as I'm using a standard coordinate system, which I have no reason not to, what I'm going to do is I'm going to look at this picture and say, I want everything to be along x or y. And anything that is not along x or along y, I need to break into components. And so what I'll say is, let's split this up. That the Falcon's initial velocity, I'm not going to use VFI. I'm going to say the Falcon's initial velocity in x and the Falcon's initial velocity in y. And for the final, I could just say 1v final because they get stuck together. But I don't want just 1v final. I want 1v final in x and 1v final in y. And I'll just split it down. The initial component of the velocity, the initial component of the Falcon's velocity in x is just going to be the magnitude times cosine, which I can plug in my numbers and get a value. The initial component of the initial velocity of the Falcon in y, I'll just use sine of the angle as long as you measure from the horizontal. And I can just plug in some numbers and get a value. And I can say screw VF comma I. I want VFIX and VFIY. I want to know its x and y components. That this vector right here is actually pretty useless. And so I'm not going to use it. That's the numbers I want to use. So I'm going to get rid of this V Falcon initial is 18 meters per second and the angle, and I'm going to replace them with my x and y components. Once again, I don't need to do this for the pigeon because the pigeon is only an x. He has an x component of velocity and no y component whatsoever. But what I can say is that momentum is conserved. But not only is momentum conserved in general, but I can just treat it as vectors. Conservation of momentum in x, conservation of momentum in y. And I'll go through both of them. I'm going to start with x because reasons, as in I don't have any. And I'll say just looking at my vectors, I'll say in x, I have this initial in x. I have this initial in x. And I have a final in x. And so in x, I'll say my initial is the x component of the Falcon plus the pigeon, and my final is them added together. If I divide both sides by that total mass, I'll get the x component of the velocity when they're stuck together. I'll just plug in some numbers and solve. But that's just the x. I can say in y. In y, I have, that's not doing anything what I want to do. This is what I want to do. In y, I have the Falcon initial, and the pigeon's not doing shit in y. He has no piece here. So nothing from him. But I do have a final in y. And so in y, I would say I have the Falcon's component, nothing from the pigeon, and my final. And if I divide both sides by my total mass and plug in some numbers, I'll get my y component. But here's the thing. If you tell someone that it's moving at 11.6 meters per second in the x direction and at negative 8.78 meters per second in the y direction, no one's going to care. We need, as physicists, to work in x and y. But as human beings, we don't work that way. We want magnitude and direction. But the thing is, if you know the x and y direction, you can get the magnitude and direction. To get the magnitude, we've been doing this since chapter 1. It'll just be the square root of x squared plus y squared, where I can plug in my values, do that math. If you want direction, direction is the inverse tangent of y over x, where I can plug in my numbers and get a value. Okay? Let's do one more. My last one is going to be about curling. Because why not? Curling is dumb. Back when I lived in Buffalo, I actually used to go across the border to Canada to go curling because a Canadian convinced me to, and it was stupidly fun. Curling is just 2D collisions. What curling is really is this. You slide a hunk of granite down ice and hit other hunks of granite and watch them deflect off each other. Let's look at a simplified thing with just one stone hitting another stone. And not all these things going happen. You gotta love how it has a Tim Hortons logo too for curling. So stereotypical. So we have a red curling stone of mass 16.2 kilograms with a horizontal velocity of 3.51 meters per second. Hits a yellow curling stone of mass 12.3 kilograms initially at rest. But it doesn't hit it straight on. It hits at a slight angle. Because it hits at a slight angle, after the collision, the yellow stone moves at 3.67 meters per second at an angle of 23.21 degrees below the horizontal. What is the velocity, magnitude, and direction of the red stone? So all of my numbers are written right on this figure. I have to admit, I just found this figure and made the problem around it. And so I'm going to say those are the numbers I need. That my mass of red, my mass of yellow. My velocity red initial, 3.51 at 0 degrees. My velocity of yellow initial is 0. My velocity of yellow final, and I'm once again just doing a negative angle to make my life easier. See, I can say initial momentum equals final momentum, or momentum equals mv. But this is two-dimensional again. If an angle shows up, you got to deal with it. And so I'm going to say really two equations, one in x, one in y. And that all of my velocities need to be broken into the x and y components. Now the red one is easy. He's at 0 degrees. And so all of his velocities at x. There's none in y. This yellow one is a little more complicated. I need to split it into its x component and its y component. Well, really that's the same as me drawing this guy here and just moving this over there, just like we did in forces. And so for the yellow one, I would say, okay, we can get the x component. I'll just do magnitude cosine of the angle. And I can get the y component. That's his magnitude sine of the angle. Now, there is a slight thing here that I fully acknowledge is kind of messy, so I want to address. And that is I have yellow and y. This is one of the biggest issues with these problems. Be careful with your subscripts. Because I decided to call it velocity yellow final in x and velocity yellow final in y, if you just look at it quickly, you might think this is the velocity in y because there's a v sub y. It was kind of a mistake of me just picking yellow and red because I stole the figures before putting thought into it. Be careful with your subscripts. Do things that make sense to you. And just, yeah, be careful. But either way, I have my yellow puck or yellow stone broken into components. The x component and the y component for the final velocity. And I'll say initial momentum equals final momentum. I'm going to do x first for no apparent reason. And I'll say initially in x, we have the momentum of the red. Final in x, there's momentum of both the red and the yellow. And I can solve for the final velocity of the red in x. I'll subtract yellow's final momentum from both sides and divide both sides by the mass of the red stone. That'll allow me to put in numbers and do the math. And I'll just take that and put it to the side. So that's half the problem. I solved the x problem. Now that I solved the x problem, I'll solve the y problem. And I'll say initially in y, well, initially in y, nothing's happening. The yellow puck isn't moving, and the red puck is only moving in x. So initially in y, there is no momentum. But final in y, they both have momentum. I'll subtract the yellow from both sides, divide both sides by the mass of red, and plug in my numbers, which will give me a value. My negative signs cancel out since yellow's final was negative. And I'll put that to a side and say my goal was to find the final velocity of the red. And here is, I have its x component, I have its y component. If I have its x and y component, I can easily put it together. Pythagorean theorem to get the magnitude. And to get the angle is just the inverse tangent of y over x. And there's my answer. Two-dimensional isn't any hurdle per se. It just takes longer to do. It's just more work because you got to do the problem twice. But conservation momentum is very simply straightforward. You just look at a picture, look at all the arrows, and say your initial momentum equals your final momentum. And once you have your initial momentum and your final momentum, you set them equal to each other. Okay. Questions? Okay. The good news is that momentum isn't really that complicated. I know some of you might still need a little bit of practice to get through it, but I'm just like, in the way of this class is one of the most simpler ideas. What that means is that is everything on momentum. There is nothing else I have to teach you about momentum. And we're only halfway through today's lecture. We're going to end very early today because momentum is simple. This is just a shorter chapter. It's got to, like, even when we're in person, this chapter always ends super early because it's a simple idea. But what to keep in mind, and I'm not going to bother pulling up the poll, I'm just going to say it. In any collision, you can always say momentum is conserved. In a perfectly elastic collision, you can also say kinetic energy is conserved. But don't dwell on that. In a collision, don't worry about kinetic energy. Just look at momentum. But as I said, I'm going to end early. I guess I'll go into my office hours early just because I might as well. But I will, stop there. So have a good day.